The origins of the universe. From Lemaître to modern cosmology in the wood-paneled chapel of the Catholic University of Leuven in Belgium. A priest lights a candle and kneels before the statue of Christ for his daily devotion. His name is Georges Lemaitre, and the year is 1927. As he rises, his eyes wander toward the tall chapel windows and the stars beginning to twinkle in the evening sky. He smiles, reflecting on the immense journey those photons must have made to reach Belgium. Lemaitre was no ordinary priest, a Catholic clergyman devoted to faith. He was equally committed to science. He believed the universe did not need a miraculous 7-day creation, but could be explained through mathematics and natural laws. His extraordinary insight would make him one of the fathers of modern cosmology, earning him 2 Nobel Prize nominations. The primeval atom in Leuven-Lemaitre worked on a daring idea. The universe was expanding. If space is expanding now, then running the clock backwards suggests a time when all matter and energy were compressed into a single, dense state. He called this the primeval atom. This vision was not theology disguised as physics. It was a bold mathematical deduction drawn from Einstein's general relativity. Lemaitre imagined the universe's history in reverse. Galaxies contracting, stars vanishing, chemical elements simplified back into hydrogen and helium, until eventually all matter was crushed into radiation and energy. What happened before that first instant, he admitted, was a mystery even mathematics could not penetrate. Yet the insight was revolutionary. The universe had a beginning, resistance and support at the time. Most astronomers were hesitant to embrace such an idea. The dominant view was of a static, eternal universe. Fred Hoyle, one of the era's most vocal skeptics, dismissed Lemaitre's model as pseudoscience, and mockingly coined the term Big Bang as an insult. To Hoyle, the theory reeked of theology, of trying to smuggle the Genesis creation story into science. Lemaitre, however, was comfortable keeping religion and physics separate. His equations did not need divine validation. What they needed was observational proof, and that proof came from Edwin Hubble. Hubble and the expanding universe in the late 1920s from the Mount Wilson Observatory in California. Hubble peered through the world's largest telescope at faint smudges of light. Careful measurements revealed these were not stars within our galaxy, but entire galaxies themselves, far beyond the Milky Way. Even more surprising, the light from these galaxies was redshifted, stretched toward longer wavelengths, as if the galaxies were moving away. This cosmic recession was not random. The farther away a galaxy was, the faster it receded. The only explanation was that space itself was expanding. Precisely what Lemaitre's equations had predicted. The universe was not static. It had a dynamic history. The smoking gun, cosmic microwave background, the Big Bang model gained powerful support in 1964, when Arno Penzias and Robert Wilson at Bell Labs stumbled on a persistent background noise while calibrating a radio antenna. At first, they blamed pigeons roosting in the dish, but cleaning didn't help. Eventually, They realized the faint signal was cosmic in origin, the cooled, stretched radiation from the hot, dense early universe. This cosmic microwave background, CMB, matched predictions from Big Bang cosmology. Once, the universe had been hot enough for matter and light to mingle. As it cooled, photons escaped, leaving behind a faint afterglow still detectable today, only a few degrees above absolute zero. With the discovery of the CMB, the Big Bang moved from speculation to the leading scientific model. The problem of the beginning, but one problem remained. What exactly happened at the beginning? Lemaître had imagined the primeval atom. Others described it as a singularity, a point of infinite density and temperature, similar to the center of a black hole. But infinities make physicists uncomfortable. If the universe really began as a singularity, why is the cosmos today so smooth and uniform? Why are galaxies distributed evenly rather than clustered in chaotic lumps? This led to a new idea: cosmic inflation. Inflation and the early universe. In the 1980s, physicists proposed that in its earliest moments, the universe underwent a burst of exponential expansion. Space itself doubled in size again and again, faster than the speed of light. Inflation smoothed out the wrinkles, explaining why the universe looks uniform on large scales. But inflation, too, raised new questions. Why did it start? Why did it stop? Some physicists argue that if you reverse inflation mathematically, the universe never quite shrinks to zero. Perhaps the universe never emerged from a singularity at all. Hawking and the no-boundary proposal in 1981. At a Vatican conference, Stephen Hawking presented a radical idea. The universe, he said, is finite but without boundaries. Asking what came before the Big Bang is like asking what lies south of the South Pole. The question itself has no meaning. In Hawking's no-boundary proposal, space and time curve smoothly back on themselves. The Big Bang wasn't a singular beginning, but more like a rounded surface where time gradually emerges. This proposal astonished the scientific community, offering a way to avoid the infinities that plagued earlier models. Cycles, bounces, and other universes. Other cosmologists have speculated that the Big Bang was not the beginning, but a transition. The Big Bounce theory suggests the universe eternally oscillates between expansion and contraction. When it contracts, quantum mechanics allows it to tunnel past, collapse, and bounce back into expansion. Roger Penrose proposed a different cyclical idea: conformal cyclic cosmology. He argued that the end of one universe, when black holes evaporate and scale ceases to matter, is equivalent to the beginning of the next. In this view, our Big Bang was simply the handover between two cosmic eons. Still, others look to string theory for answers. Edward Witten, S. M theory, describes an 11-dimensional reality where our universe is a 3-dimensional brain, floating in higher dimensional space. Collisions between brains could spark Big Bang-like events, a radical idea known as the Ekpyrotic model. The limits of knowledge, each of these theories: inflation, no boundary, Big Bang, events, cyclic cosmology, string brain collisions, represents humanity's effort to peer behind the curtain of the Big Bang, yet none are proven. Observations of the cosmic microwave background, galaxy distribution, and gravitational waves may eventually tip the scales in favor of one theory. But the very first moments of the universe may always remain hidden beyond the reach of science. Lemaître himself would not have been troubled by this. He once wrote that there is no conflict between religion and science, because they ask different questions. Science asks how the universe works. Faith asks why it exists at all. Conclusion. From a Belgian chapel in 1927 to the vast laboratories and telescopes of today, the search for cosmic origins has transformed our understanding of reality. Georges Lemaître's vision of an expanding universe has been vindicated, but the deeper mysteries remain unsolved. Was there a singularity, an inflationary burst, an eternal cycle of bounces, or an unseen higher dimensional collision? Perhaps, as Stephen Hawking suggested, there is no before to speak of. Perhaps the Big Bang is simply the edge of human comprehension. What is clear is that the universe has a history, stretching 13.8 billion years, from a hot, dense beginning to the galaxies and stars we see today. And while we may never fully grasp what lit the first spark, the search itself is a profoundly human endeavor, a journey of imagination, mathematics, and wonder, reaching ever closer to the origin of everything.